In the last module, we saw that number theory can be useful for key exchange. In this module, we will review some basic facts from number theory that will help us build many public key systems next week. As we go through the material in this module, it might help to pause the video from time to time to make sure all the examples are clear. So as I said, we're going to use number theory to build key exchange protocols, we're going to use number theory to build digital signatures, public key encryption, and many other things. But before we can do all that, we have to review some basic facts from number theory, and in fact in this module we're going to do a quick course on the relevant concept. If you'd like to review some of the material discussed in this module offline, I reference at the end of the module a free textbook by Victor Shoup, and I point to some specific chapters in this book that will explain the material that we will cover here. So from here on I'm going to use the following notation. I'm going to use capital N to always denote a positive integer, and I'm going to use lowercase p to always denote a positive prime number. Now I'd like to introduce the following notation. There's this funny z that's written like two diagonal lines here with a subscript n. I'm going to use that to denote the set 0, 1, 2, up to n minus 1. This is actually very common notation that's used in crypto, and so I'll stick to that here. So again, z sub n denotes the set of integers 0, 1, up to n minus 1. And in fact, this is not just a set of integers. We can do addition and multiplication in this set as long as we always multiply modulo the number n. For those of you who know a little bit of algebra, I'll just say that z sub n denotes a ring where addition and multiplication are done modulo n. This is very common notation in crypto, although in modern mathematics, z sub n sometimes denotes something else. But as I said, I'm going to keep on using z sub n to denote the set of integers 0 to n minus 1 with addition and multiplication modulo n. So I want to make sure everybody is comfortable with modular arithmetic. And so let's just look at the number, say, n equals 12. And let's just see some basic facts about modular arithmetic. So I'm going to say that 9 plus 8 is 17. 17 is 5 modulo 12. So I'm going to write that 9 plus 8 is equal to 5 in Z12. Now, can someone tell me how much is 5 times 7 in Z12? In other words, how much is 5 times 7 modulo 12? Well, 5 times 7 is 35. And if you recall, 36 is divisible by 12. So 5 times 7 is really minus 1 modulo 12. 35 is minus 1 modulo 12. But minus 1 modulo 12 is basically the same as 11, because I just add 12 to minus 1 and I get 11. And the next question is, how much is 5 minus 7 in Z12? Well, 5 minus 7 is minus 2. Minus 2 modulo 12, well, I just add 12 to minus 2 and I get 10. As a result, we say that 5 minus 7 is equal to 10. So again, this is just to make sure everybody's comfortable with this notation of working in Z12. In other words, working modulo 12. Now, I'd just like to make a general statement that in fact, arithmetic in Zn, in other words, arithmetic modulo n, works just as you would expect. So for example, all the laws that you know about addition or multiplication work equally well in Zn. For example, the distributive law, x times y plus z, is still going to be equal to x times y plus x times z. So many of the things that you know about arithmetic when working over the integers or in the reals will translate to working in Zn, namely working modulo n. So the next concept we need is what's called a greatest common divisor, or a GCD. And so suppose I give you two integers x and y. We say that the GCD of x and y is basically the greatest common divisor. It's the largest number, the largest integer that divides both x and y. So for example, what is the GCD of 12 and 18? Well, the GCD is 6 because 6 divides both 12 and 18, and it's the largest number that divides both 12 and 18. Now there's an important fact about GCDs. In particular, if I give you two numbers, two integers x and y, there will always exist two other integers, I'll call them a and b, such that if I look at a times x plus b times y, what I get is the GCD of x and y. In other words, the GCD of x and y is a linear combination of x and y using the integers a and b. So let's just look at a simple example. Here, let's look at our GCD from before. So the integers for this GCD would be 2 times 12 minus 1 times 18. That's 24 minus 18, which is equal to 6. So the integers a and b in this case would be 2 and minus 1. But this is just an example, and in fact these integers a and b will exist for any integers x and y. Now, not only do a and b exist, in fact there's a very simple and efficient algorithm to find these integers, to find a and b. The algorithm is what's called the extended Euclidean algorithm. This is actually one of the prettiest algorithms from ancient Greek times, due to Euclid, of course. I'm not going to show you how this algorithm works here. It's a fairly simple algorithm. I'll just tell you that, in fact, given x and y, this algorithm will find a and b in time roughly quadratic in the logarithms of x and y. And we'll come back to that and discuss the performance of Euclid's algorithm in a bit more detail in just a minute. But for now, all we need to know is that a and b can actually be found efficiently. Now, if the GCD of x and y happens to be 1, in other words, 1 is the largest integer that divides both x and y, then we say that x and y are relatively prime. For example, the GCD of 3 and 5, it's not difficult to see that that happens to be 1 because both 3 and 5 are prime. The next topic we need to talk about is modular inversion. So over the rationals, we know what the inverse of a number is. In other words, if I give you the number 2, the inverse of 2 is simply the fraction 1/2. The question is, what about inverses when we work modulo n? Well, so the inverse of an element x in Zn is simply another element y in Zn such that x times y is equal to 1 in Zn. In other words, x times y is equal to 1 modulo n. And this number y is denoted by x inverse. And it's not difficult to see that if y exists, then in fact it's unique. And as I said, we'll use x inverse to denote the inverse of x. So let's look at a quick example. Suppose n is some odd integer, and I ask you what is the inverse of 2 in Zn. So it's not too difficult to see that the inverse of 2 in Zn, in fact, is n plus 1 over 2. And you can see that this is an integer because n is odd, therefore n plus 1 is even, and therefore n plus 1 over 2 is in fact an integer in the range 1 to n as required. Now why is n plus 1 over 2 the inverse of 2? Well, let's just multiply the 2. So we do 2 times n plus 1 over 2. And what do we get? Well, that's simply equal to n plus 1, and n plus 1 is simply equal to 1 in Zn. So since their product is equal to 1, we know that n plus 1 over 2 is the inverse of 2 in Zn. Now that we understand what a modular inverse is, the question is which elements actually have an inverse in Zn. And so there's a very simple lemma that says that if for an element x in Zn, that element has an inverse if and only if it is relatively prime to the modulus n, to the number n. So I'll say that again. X in Zn is invertible if and only if x is relatively prime to n. Now let's quickly prove that. It's actually fairly simple to see. So suppose the GCD of x and n happens to be equal to 1, so x is relatively prime to n. Well, by this property of GCDs, we know that there exist integers a and b such that a times x plus b times n is equal to the GCD of x and n, which happens to be 1. So a times x plus b times n is equal to 1. Now, we can actually take this equation here and reduce it modulo n. So what this means is that a times x is equal to 1 in Zn. Once we reduce this equation modulo n, this term simply falls off because b times n is divisible by n, and therefore is 0 modulo n. But what we just showed is that in fact x inverse is simply a in Zn. So because x is relatively prime to n, we were able to show that x is invertible by actually building the inverse of x modulo n. Now what about the other direction? What happens if the GCD is greater than 1? Then we want to show that there is no inverse. But that's actually very easy to see because in this case, if you claim that a happens to be the inverse of x modulo n, well, let's look at a times x. A times x we know should be equal to 1 modulo n. But if the GCD of x and n is bigger than 1, then the GCD of a times x and n is bigger than 1. But if the GCD of a times x and n is bigger than 1, then it's not possible that a times x is equal to 1. So a times x must also be bigger than 1, and therefore a cannot be the inverse of x modulo n. So this proves that in fact when the GCD is greater than 1, x cannot have an inverse because there is no a such that a times x is equal to 1 mod n. And this might be a bit confusing, so it might be best to do an example. So let's suppose that the GCD of x and n happens to be equal to 2. I claim that x is therefore is not invertible modulo n. Well, why is that true? Well, for all a, we know that a times x is going to be even. And the reason we know that is because, well, 2 divides x and 2 divides n. Well, since 2 divides x, 2 is also going to divide a times x, and therefore a times x must be even. But what that means is that there's no way that a times x is equal to 1 modulo n. In particular, there's no way that a times x is equal to b times n plus 1. This simply can't happen. This equality must not hold, because this side happens to be even, as we said. B times n, for exactly the same reason, is also even. N is divisible by 2, therefore b times n is also divisible by 2, but therefore b times n plus 1 is odd. And since even can't equal to odd, it's not possible that a times x is equal to some multiple of n plus 1. And in particular, this means that a cannot be the inverse of x, because a times x cannot be 1 mod n. So x is not invertible modulo n. So now we have a complete understanding of what are the invertible elements. Basically, we know that an element is invertible if and only if it's relatively prime to n. And what I like about this proof is I would say this is what's called a computer science proof, in the sense that not only does it prove to you that the inverse exists, it also shows you how to efficiently calculate the inverse. And the way we calculate the inverse is basically by using this extended Euclidean algorithm to find the numbers a and b. And once we found the numbers a and b, we're done, because a is the inverse of x. And the numbers a and b can be found very efficiently. So along the way, I've also shown you an algorithm for inverting elements modulo n. Okay, so bear with me and let's introduce just a little bit more of notation. So we're going to denote by Zn star as the set of invertible elements in Zn. In other words, Zn star is the set of all elements in Zn such that GCD of x and n is equal to 1. Okay, but I want you again to think of Zn star as basically those elements in Zn that have an inverse. So let's look at a few examples. So let's start with a prime p. We know that of the integers from 0 to p minus 1, all of them are going to be relatively prime to p, except one integer, namely the integer 0. 0 is not relatively prime to p because the GCD of p and 0 is 0, not 1. So therefore, if p is a prime, the set zp star is simply zp minus 0, which means that everything in zp star is invertible except for 0. So if you like, the size of zp star is simply p minus 1. Now let's look at our favorite integer again. So why don't you tell me what is z12 star? What is the set of invertible elements modulo 12? And the answer, of course, is all the numbers that are relatively prime to 12, namely 1, 5, 7, and 11. So for example, 3, 4, 6, all of those are not invertible because they all have a non-trivial GCD with 12. And as we said before, if I give you an element x in Zn star, you can find its inverse using the extended Euclidean algorithm. You can find its inverse very efficiently, in fact, using this algorithm. So what we just learned is basically how to solve modular linear equations. In other words, if I give you a linear equation and I ask you to solve it mod n, it's actually very easy to do. All you do is you move b to the other side, so you have a minus b, and then you multiply by a inverse. So the answer is minus b times a inverse. And you can find a inverse using the Euclidean algorithm. And once you have a inverse, you'd simply multiply it by minus b modulo n, and that gives you the solution to this linear equation. Now, the Euclidean algorithm actually takes time that's quadratic in logarithm of n. So it takes time proportional to log squared n. And as a result, we say that this is a quadratic algorithm for solving linear equations modulo n. And in fact, this is the best known algorithm. And so if you think back to your high school algebra days, after you learned how to solve linear equations, the next question was, well, what about quadratic equations? And that problem is actually quite interesting, and we're going to see that in the next few segments.